Thank you very much for the invitation. It's a pleasure to be here, first time in Lithuania. And I'm positively surprised how pleasant the country is so far. And they tell me that in the city center it's going to be even more impressive, so I'm looking very forward to seeing that. Okay, so I'm an ICREA professor at the ICFO, which is the Institute of Photonic Sciences, outside Barcelona. It would be unforgettable if I don't advertise the positions for PhDs in our institute. So anybody who wants to apply, please do, because we are continuously looking for good students. So in my group and in other groups as well. Also, I understand that this is going to be posted on YouTube. It's very hard to imagine that this is going to make a big hit, but anyway, I think maybe it's useful for other people who want to see this. So I realized also that the topics covered during this conference are very varied. So it's a broad range of topics. So I don't want to sound too specialized on a very specific thing. Therefore, I'm going to try to make it very tutorial, focusing on concepts. And rather than going directly to graphene, plasmons, and metamaterials, I will start introducing the subject. First of all, why do you need to control light at the small distances compared to the light wavelength? And that's what metamaterials and also plasmons are about. And so I just copied here a few images that illustrate what we can do nowadays with light and by controlling light at the small distances. Optical lithography, so you basically imprint, possibly via some nonlinear processes, you imprint a circuit on a chip. You can do also optical trapping. I think this is now a routine. If you want to study biological cells, human cells, for example, you can trap them with a laser beam, and then they get attracted by the light. Also photovoltaics. So there are lots of groups who are trying to improve the efficiency of solar to electricity conversion, energy conversion, by decorating a material with a small structures, and in particular with structures that sustain plasmons. I will explain in a couple of minutes what that is. This is another use of controlling light at small distances, which is cancer therapy. In this case, basically what you do is you mark metal nanoparticles, so they are attached to tumoral cells, and then you illuminate those cells with infrared light. Infrared light that has a depth of penetration of about 8 centimeters or so, at 800 nanometers inside our bodies, and therefore you hit the nanoparticles and then kill the cells, only the tumoral cells. Also for single molecule sensing, and I will present a couple of examples of this. So first of all, let me introduce this fundamental problem. I think there is room there, so for those who are standing, plenty of room over there. So this is the problem of diffraction, the diffraction limit. So you want to image things that are very small. You want to produce features on a material that are very small, certainly much more than the light wavelength. And so how to do this? So basically, you have a wave that is coming with a certain angle on a surface, and through that wave you want to image or to imprint a pattern on a surface. So that's the wave vector of light at a certain wavelength, and that's the projection of the wave vector, which is even smaller than the light wave vector. So then what I've done here is, I think this is a tutorial slide. Basically, this is the integral of components. Each of these components is like a cosine wave. So you collect many of these components from k-pairs between a certain maximum range. And then this range is expressed here in terms of the light wave vector. Of course, if you use light from the far field focused on a surface, then you can only do that with parallel wave vectors that are smaller or equal than the light wave vector. Because essentially, for larger wave vectors, then they don't propagate. They are evanescent. So you can see here what's the diffraction limit. Essentially, if you use this value for this integral, then you get a feature that has approximately the size of half a wavelength, and that's how far you can go with propagating light. Okay, so you want to do better than this. You want to do small features. You want to concentrate light down to small regions, and for doing that, you need wave vectors that are much larger than the light wave vector, maybe 10 times larger, and then you have really, really small features, much more than the wavelength. Okay, why this is practical? Well, you see, when they produce the, microchips now in the steppers, they go through all the trouble of moving the silicon wafers with a nanometer precision laterally and at the speeds of meters per second, and they do that to imprint an optical field with the best possible features, that is the smallest possible wavelength. And they do that in water, so the whole thing is embedded in water, simply because water at this wavelength, which is the one used, the shortest intense laser that is used nowadays, so water has this index of refraction, so the wavelength is reduced by this much. And this gain in resolution, this reduction in the wavelength, compensates to go through all the trouble of moving everything in water. Okay, so of course this is a way of reducing the wavelength, the size of your features, but is limited because you cannot get very high index of refraction in a material. So there are other ways, and other ways is essentially if you want to achieve a parallel wave vector that is much larger than the wave vector of light in this direction, because of the conservation of the total wave vector has to satisfy this relation, so that's the wave vector of the light. So that means that the perpendicular wave vector, the perpendicular component, has to be imaginary, just to compensate. And imaginary means evanescent waves. So by using evanescent waves, then you naturally produce larger, a higher resolution. And this is essentially what's done, for example, with a near-field tip, just concentrating physically light down to a small region in space. So generally, you can do this. You want to concentrate light down to a small region just to produce this ultra confinement. Just and then one way of doing that is with a single of a few electrons, for example, in metals, right? If you imagine a single atom and then the cross section for a single atom, a good two-level atom like I don't know, erbium. So it's going to have a cross section that is approximately the square of the wavelength, divided by 2. It's a huge cross section. However, it's not a very robust object, because when you put it close to any material surface, then its response completely disappears. So you need something that is more robust. So essentially you need more electrons to construct more robust excitations, and this is how the plasmons come about, and that's a central concept in metamaterials. So how to control light down to small scales is basically through plasmons. So plasmons are robust. If you put a metallic nanoparticle close to a metal surface, then the metal nanoparticle will still have intense plasmon resonances. If you put a two-level atom close to a metal surface, then the two-level resonance disappears. It just gets destroyed by interaction with the medium. So this is what a plasmon is in a very tutorial way. Imagine, for example, you have a gold nanoparticle, and then you have conduction electrons, and now with the light coming from, for example, with this laser, you have an electric field associated with the light, and the electric field is moving the electrons, just the action of the electric field on the electrons. So these electrons are displaced with respect to the equilibrium position, and now there is a restoring force with the positive ions left behind. And now this restoring force is going to set up a spring motion. Like any spring, it has a natural frequency. And now what happens is, for when you have materials which are gold or silver or noble metals, and where the size of the particles is tens of nanometers, then you can have resonances in the visible, in the near infrared, and they are useful for technology because those are the ranges where we use them for technology, for sensing, for optical signal processing, etc. So this is already used without knowing, and this is actually well-known slide of plasmonic nanoparticles in 4th century Rome, where they knew how to produce colors in glass by putting in the glass some salts that had some content of gold and silver. Okay, so it turns out that this glass that is on exhibit in the British Museum, so on reflection you see it greenish, on transmission you see it reddish, and this is because you have metal nanoparticles inside, so these nanoparticles will essentially scatter light, essentially scatter green light, and therefore also deplete all of the green light, so on transmission is reddish. Okay, so they used this, but they didn't know. So, and also you see metal nanoparticles were already produced long ago. Of course, we have gone a long way, and now we are capable of controlling much better the size of the particles, to have monodisperse particle dispersions. For example, here with different sizes, you see experiment and theory. It's difficult to tell which one is which because the agreement is nowadays quite good. And essentially, you have also the plasmon resonances, which have an associated electric field. As these conduction electrons move throughout the nanoparticle, then we'll set up, for example, in this case, a dipolar mode, and eventually it becomes more quadrupolar. So that's how you see here, when you go from a small nanoparticle to a larger nanoparticle, then you have a dipolar mode and eventually a quadrupolar mode. So the physics of the response, optical response of nanoparticles is by now well understood. And then many of these features we really understand. You have also good control over the shape of the nanoparticles. They can be anisotropic. For example, here with nano rods in a colloidal reaction, where you stop the colloidal reaction at certain stages, and then you stop the colloidal reaction there, and then you come up with particles that have this shape or this shape. Eventually, this is isotropic. And then, for example, here you have one mode that is oscillating in this direction, which is this one, another one that is oscillating in this direction, which is much faster, so a smaller wavelength. And as the particle becomes thicker and thicker, the two features basically coalesce into each other, and eventually the particle becomes isotropic, so it has only one mode. Okay, so these type of things are well understood. I've been showing some maps of the plasmons, and then we would like to visualize them. So we would like to visualize them. What can we do to visualize the plasmons? Because these features that I show here, you see the distance, the size of the particles here is 12 nanometers. This is much more than the light wavelength, which is 500 nanometers. So with an optical microscope, you cannot visualize this sort of plasmons. So here is a collection of different techniques that are used to resolve excitations, optical excitations, that are organized as a function of the spatial resolution and also the excitation energy that they target. So you have some of these techniques that are based on optics here. Some others are based on electrons, essentially here. And you see within this energy range, then the electron wavelength is much more than the photon wavelength, and that explains that these techniques that are based on electrons, they achieve a much better spatial resolution. So one way to visualize the plasmons is essentially by using electrons instead of light. So, okay. Then I will conclude this introduction on plasmons as a motivation for graphene plasmons and graphene metamaterials by just explaining when you have an electron, then the electron carries with itself an electromagnetic field, and that also interacts with our nanoparticles. Therefore, you produce an optical interaction. You can probe the optical excitations in the nanoparticle. If I see an electron coming here, then I am the particle, so I will see an electric field that is going up and then eventually down. So it's a function like this. If I do the Fourier transform, if I look at a specific frequency component of this field, then it will have an evanescent character. So close to the electron, I will have an evanescent field. It has to be evanescent because otherwise it will radiate. We know there is no such a thing as radiation coming from a freely moving charge, like Cherenkov radiation in vacuum or something like this. Okay, so that's a fantastic probe because it has an evanescent field close to the electron trajectory, and this is actually has been used over the last 10 years or so to probe these plasmons. So here you see this silver nanoprism. Is also very small, and then you see that there are different modes that can be probed. First of all, you send the electron at one position, for example here, and then you see a spectrum like this. So there is one mode like this, and you send it somewhere else, and then you see a different spectrum, and again here a different spectrum. So now you scan the beam and then collect the spectra as a function of the position of the beam, and then plot the intensity of these features. That's what you get. So these are snapshots of the plasmons with the resolution that is just a few nanometers in size. So that's the best combination of energy space resolution that there is for photonic excitations. This is more recent work from a group of Luis Marzán in Biomagune in San Sebastian. So basically, they were able to produce these nanowires with good monodispersity. So that means lots of them in dispersion, but with a size that were well controlled, with a small size dispersion. And then you see here spectra. One of them is the theory, the other is the experiment. Again, difficult to tell apart. So we basically understand the different modes of these resonances in these nanowires, but how they are. So this is experiment, this is theory. With electron energy loss spectroscopy, again, you can visualize all of these excitations, dipolar, quadrupolar, etc., all of them. Okay, so these plasmonic modes. With a resolution that is, well, the size of these nanowires is 34 nanometers in diameter. So impressive resolution. Finally, you also have electrons that can be impinging on a surface, on a target, and then as a result of that, then you also produce light emission, and the light that is emitted can be also used to probe these excitations. This is work from Albert Pollmann in Amorph, and then basically they were able to probe plasmon modes that were circulating in these circular grooves. Okay, and then comparison with theory just allowed us to ascribe specific symmetry for the different modes, like azimuthal symmetry, m equals 1, 0, etc. Okay. So far for the introduction. Now I move to the new type of materials, and then, but I thought that was needed given the broader scope of the conference. So basically, the take-home message for plasmons is the following. Plasmons have the following appealing properties. They concentrate light down to a small size compared to the light wavelength. So all of these particles that I've shown you are much more than the light wavelength, basically tens of nanometers in size. No? And also the field enhancement that they produce. So the field associated with the plasmon can be orders of magnitude higher than the external field provided by the external illumination. Okay, I will emphasize this a bit more. Just again, I hope this is sufficiently tutorial. This is a very prototypical plasmonic structure consisting of two metal nanoparticles separated by a narrow gap. Now, when you illuminate this with light, again, this is the external field provided by the light, perhaps it's laser, then you set up a dipole, basically polarization charges, plus minus, because the object is large, and especially if it is on resonance, then you can have a strong polarization. But now, because the system is such that you have charge neutrality in each of the particles, you have to compensate this charge with an opposite charge near the gap. Okay? And now these two charges will be separated by a small distance, so the dipole that they produce is very small. The light doesn't couple too much to this component of the polarization charges, But because they are separated by a small distance, it's like in a capacitor, you fix the charge through here, and then when you decrease the distance, then the electric field in between increases, and it can be orders of magnitude higher than the field that you apply. So this is a result that we published a few years ago, on which we reproducibly were able to detect and also identify the chemical nature of certain molecules that were sandwiched in between a metal nanoparticle and a metal surface. So just by looking at individual molecules and then looking at the trace that the scattering by the molecule produces. And this is inelastic scattering, so it's like a barcode that identifies the frequencies of the vibrational features that identify what is the molecule that you are talking about. So these are so-called hotspots. This is a hotspot. So essentially with a plasmon you produce a region where the electric field is amplified by many orders of magnitude. According to this experiment, the conclusion was that the intensity here was 5 orders of magnitude higher than the one applied from the external laser. So you can have many nanoparticles like this in a random arrangement, and then you produce lots of hotspots, no? in a random way, essentially. Okay, finished. Now, I'm going to talk about a completely different thing, but it has to do with plasmons, which is I'm going to try to convince you that there is new physics emerging when the number of electrons that are engaged in the plasmon are small. So when only a few electrons, not like in a large nanoparticle where you have millions of electrons engaged in the plasmon motion, but when you have something that is small, for example, ultra thin, then something else will happen. And essentially, graphene is the material that made this possible. So you can have resonances in the graphene, resonances that are plasmonic, similar like with metal nanoparticles, but now the material is only an atom thick, and therefore the number of electrons that are involved in each of these patches here is very, very small, much more than in the metal nanoparticle. I think we'll go through that. So there are a number of applications that people have been expected over the last few years. Some of them are coming closer to reality. Some of them are a little bit fantasy still, but anyway. So one of them was the modulation of light. So the ability to modulate light by applying an electrical voltage. So you apply a voltage here, and then you basically imprint a pattern on the reflected light or the transmitted light or something like this. Then you can have a molecule that will produce changes in reflected light, and therefore doing this you can, for example, sense the molecule, detect the presence of the molecule. Then you have charge carrier separation, for example, for photo detection. So you can this has been speculated that with this type of material you can be very sensitive to minute amounts of light, and also spectrally sensitive, so you can produce spectra out of very dim light. Okay, so this is in chronological order a set of carbon allotropes. So we start also in order of discovery, but also in the order of dimensionality. So the fullerenes were discovered first, zero-dimensional, then the nanotubes, then the graphene. So all of them, they share in common these features taken from the literature and these references. So they have so-called pi plasmons and sigma pi plasmons, and they occur at relatively high energies. So this is 5 eV and 15 eV, so the visible just is somewhere here, okay, and the infrared is even farther below. Okay, so these are UV resonances in this case. Okay, these are not going to be the resonance I'm going to talk about, but anyway, they are interesting, and there was a group here, Hydrobo, in Oak Ridge, who were able to map these plasmons and the trapping of these plasmons to a single atomic defect in the material. So they were able to essentially image a plasmon that was trapped by a defect, an atomic defect. Okay. So what I'm going to talk about is a bit different. Now, because the materials here, they involve a small number of atoms, something will change dramatically when we inject additional electrons to these materials. And then we can inject additional electrons, for example, using a gating configuration like this. It's just a capacitor. So you have a bottom gate. Typically, this is done with doped silicon. And then you have an insulator. Also, typically, this is done with oxidized silicon, the top layer, maybe 300 or 500 nanometers or something of oxide. And then you have here graphene, in this case, contacted with metallic contact. And then you apply a voltage between the bottom gate and here. So by doing that, you inject charge carriers into the graphene, just like in a regular capacitor. So what happens then is you have these features, which are the pi and the sigma plasmons that are like this here, but something else happens. There is an additional plasmon band that emerges as a result of the doping charges that you put here. Okay? So what happens when you move the potential that you apply is that this feature moves up and down. This feature moves up and down. So you essentially can tune them by applying a different voltage. So this was demonstrated a few years ago. That was in collaboration with the groups of Franz Coppens and Rainer Hillenbrand. And then you see here this same tapered ribbon. And then this is a near-field map of the plasmons with resolution that is much more than the wavelength. I forgot to put it here, but the wavelength in this case is about 10 micron wavelength, so an energy of 0.1 electron volts or so. And then by applying a different voltage here, oops, okay. By applying a different voltage, what you get is you can move the plasmon, literally move the plasmon to different positions. So at a given position, then the plasmon can be tuned on and off simply by applying a voltage here. Okay? This was unheard of in the field of plasmonics, nanophotonics in general. So let's look at the physics behind this phenomenon. So here we have a graphene layer, and then we apply an electric field, which is the electric field coming from the bottom gate in this case, so in this capacitor. And then what I put here is the band structure of graphene. So graphene near the Fermi level, it has dispersion electronic bands that are like this. So they cross the Fermi level at a single point, and they have the lower band is fully occupied in pristine graphene, and the upper band is fully unoccupied, right? So this should be more or less well known by now. I don't know to what extent this is known to other communities, the band structure of graphene. Yeah, more or less. Anyway, so near the Fermi level, the only thing that you have in graphene, the only thing that you have is this band structure. And so now you apply an electric field, then, for example, in this direction, then you will attract electrons here. So the graphene can conduct electricity, so it will attract electrons, will pile up electrons, and those electrons will fill up the empty levels up to a certain position, which is a Fermi energy relative to this point, which is called Dirac point. Because the dispersion relation is linear, so then the description of these modes can be done with Dirac equation, and they talk about Dirac point, Dirac fermions, etc. So there's a lot of nomenclature there. But the important thing is that you can move the Fermi level by a substantial amount. So with currently available gating technology, a device that similar to what I showed you before, then you can gate by about 1 electron volt. So you can change the Fermi level by about 1 electron volt of the other 1 electron volt. Okay? As a result of that, if you just collect the number of electrons you have here in a simple Drude model for the metallic response, in this case it has to be corrected a little bit because now you see the velocity of the electrons. Basically, the velocity is the derivative of the band structure with respect to momentum. So the velocity is constant. It's the same velocity, no matter what the energy is. So you take that into account, and it gives you a conductivity that has the Drude shape. So it has 1 over frequency dependence with some losses, and it has a weight that is proportional to the Fermi energy. So that means by changing the Fermi energy, you change radically the response of the graphene. Now, this is a tutorial exercise. You have a layer with a certain conductivity. Now, this layer can sustain optical modes, and then the wavelength of those optical modes is related to the wavelength of light at the same frequency, and then to the conductivity. So that's the relation between the two. And if you plug this inside here, then you get this relation between the wavelength of the plasmon modes in this graphene layer and the wavelength of light at the same frequency. And they are related through the finest structure constant. This is 1 divided by 137. That's a small number. So this is 2 orders of magnitude smaller than the light wavelength. And then you have the Fermi energy here, so this can be modulated by changing the Fermi energy. And this will be similar order of magnitude. So basically you have a strong confinement. This is much more than the light wavelength. And also you have modulation of the plasmon wavelength. So you can represent this dispersion relation in this sort of diagram. So 1 over the wavelength is the parallel wave vector. 1 over the light wavelength is the proportional to the energy. So that's the dispersion relation. And it has more or less this dependence is the square root of the parallel wave vector, and that's typical for two-dimensional systems. If you compare that to materials such as gold, then see what happens. Gold has an S band near the Fermi level. It crosses the Fermi level, and it has already a lot of states that you have to fill if you want to raise the Fermi level. So you want to change the response, then you have to put many electrons here. That's hardly achievable, in contrast to graphene, where just a few electrons can do the job much easier. Now, another feature of graphene is if you don't put any electrons at all, then you see you have for all possible photon energies, you can put 1 electron here to a hole here, so you can promote electrons from the occupied to unoccupied band for almost any energy. Photon energy. As a result of that, then you get a conductivity that is kind of universal, so it's only related to fundamental constants. For graphene, this has been already measured experimentally, and then the absorption that this produces is pi alpha, so it's again related to a fundamental constant of nature. Okay? Actually, you can use this feature, for example, to I mean, this is very small. 2 pi alpha is 2.3% absorption. It's a small quantity. If you want to really do nanophotonics out of it, you need to produce much larger absorption. One way of doing that is by putting your graphene inside a resonator, for example, here a Fabry-Perot resonator, and then if it has a quality factor that is maybe 100 or something, then it will amplify the absorption by that factor. And eventually it can go to even 100% absorption, a modulation between 100% and 0 absorption when you change from doped to undoped graphene. Okay. Then another thing that needs to be commented is you have electrons that are evolving inside the partially occupied band. So these are intraband transitions, but you have also, if the photon energy is large enough, you have interband transitions. You can promote 1 electron from here to here. So interband, intraband. Okay? Your plasmons live in the region. Oops. The plasmons live in the region that is precisely staying in this gap between interband and intraband transitions. You can see, for example, with a certain doping, then you have an optical gap. Vertical transitions have a gap that is twice the Fermi energy. So this is the gap. And eventually closes down when you consider oblique transitions, right? That's where the plasmon is, okay? Just what I'm going to do next is I'm going to discuss some of the things that we've been doing over the last few years with this material and what are the possibilities that are open. So one of the things that we've been doing is to, first of all, because graphene is such a simple material to describe, is two-dimensional, is in the electrostatic limit. That means your plasmon wavelength is much more than the light wavelength, so you don't have to care about retardation effects or things like this. essentially you don't need to care about Maxwell's equations. You are good with Poisson's equation. And then if you just solve Poisson's equation and produce the self-consistent relation for the potential set up by an external potential in response to some conductivity in your graphene, etc., then you find, you can see the details here, then you find the plasmons in this structure to be related to the Fermi energy and the size of the structure, and then there are some constants here. These constants depend on the type of shape, and then you can calculate them once and for all for a specific geometry, and then you know where the plasmons are. They are going to be, you apply this constant, and then they are going to scale with the size and with the doping according to this expression. So we need to retain this formula, so we are going to discuss very briefly what that is. One of the things that we've been doing is to try to improve this 2.3% absorption through the plasmons. So one of the things you can do is perhaps by patterning the graphene, you can actually improve this absorption. What is the maximum absorption you can achieve for an optically thin material? If you come with light with a certain amplitude 1, then you have some reflection. Also, you get some transmission. Actually, the material, if it's optically thin, doesn't care where the light is coming from. All there is are just currents induced in the material, and so it will radiate symmetrically in both directions, here and here. So you have the 1 here, and then this radiation has to be the same in both places. So absorption is 1 minus reflection minus transmission. You maximize this as a function of the complex variable R, and you find a 50% absorption maximum. Okay, so it's a simple high school exercise to get this 50%. Now the question with graphene is you can actually achieve this 50%, and you can express the whole thing analytically, and you can find it for a certain frequency related to the plasmon of your individual units, the disks here. So close to that frequency, you achieve this condition of 50% absorption. Okay. This is now a first experiment in the direction of demonstrating this high absorption. So these are graphene nanodiscs, and they are like 50 nanometers. In this image is 50 nanometers in diameter. And then what you do here is you tune through this gating device. You inject charge carriers into this graphene structure, and then by doing that, you modulate the position of your plasmon resonances. So all of this analytical theory I show you here is basically the dashed lines here, two different flavors of the theory, which compare very well with the solid curves, which are direct from experiment. One thing you can do is you can have a good mirror in this range, in this mid-infrared range. Then a good mirror will reflect the light, so light will make 2 passes through the graphene, and if these 2 passes are in phase, then you have 50% and 50% absorption, so it's 100%. So depending on the distance, on the distance between the graphene and the mirror, you can have 100% absorption. And also because the dimensions, this size, are tens of nanometers compared to wavelengths that are microns, so there is no phase associated with light propagation over these short distances. Therefore, the effect is omnidirectional. So it doesn't matter what the direction of the angle of incidence is for the light, it's going to have good absorption over a broad angular range. So these are the 2 experiments that were published a couple of years ago, also in this direction, where basically it is reported 25 or 30 or so absorption for a single graphene layer that is actually tunable. So you can tune back and forth between high absorption and almost negligible absorption. You can do other things with these plasmonic structures. For example, you can hybridize modes. You see, you have here a hole, and a hole has its own plasmon. This direction is energy. So a disk has also different plasmon, and if you put the 2 together, then the 2 plasmons will interact. And that's what you do precisely in a ring. So in a ring, you have the outer disk plasmon and the inner hole plasmon. They hybridize, and they produce a bonding and anti-bonding states. Okay, and this is perfectly seen in the experiments you see here, and also in good agreement with theory, right? So I've been talking about graphene, but there are other materials that also atomically flat in essence. Well, like the topological insulators, basically are materials that are insulating, but they have a surface band that crosses the Fermi level, so they conduct through the surface. So this layer of surface state lies in the last atomic layers. So in this case, you can do similar things. For example, here you can pattern disks, and then you can also find bonding, anti-bonding states. So it's basically very similar physics. Okay. You can also do other materials, for example, atomically thin gold or atomically thin noble metals, and then also produce good absorption cross-section. So, for example, this disk that is 20 nanometers in size, this is only theory for now. So it has an extinction cross-section. So what is the fraction, the apparent area that it extends from the incident light of the other of the area of the disk. And this is comparable to a metal nanoparticle of the same size. Okay? But in this case, it's only one atom thick structure. The idea behind this calculation was that essentially by charging this material, by charging the sphere, you can put the electrons, doping electrons here, but not enough to move the plasmon. But here, because you have so few electrons already in your atomically thin disk, then you can move the plasmon enough to modulate, right? So atomically thin materials have been produced routinely in surface science. Now the question is, one needs to merge, and hopefully that's coming in the future. So you can, by devising these types of structures where you have essentially planar metamaterial with an array of these disks, you can reach the maximum possible absorption for this planar material, which is 50% again. Okay. Another feature of graphene is that because the plasmons are so much concentrated in space, so the wavelength is very small, they have a high nonlinear response. This is something that Joel Cox from my group has been investigating over the last few years. So, for example, here you have the second order and the third order response, second harmonic and third harmonic response of graphene flakes. These are calculations, and compare with analogous results for the best nonlinear materials in this range of sizes, which are metal nanoparticles. Okay, and the graphene is predicted to be much better than any of these other materials. Similar for the wave mixing, in this case through the optical Kerr effect. If we compare different models for the graphene, so how we can understand the graphene, all of what I have told you so far is this Drude model, so this simple sigma of omega, the conductivity, and this is enough to produce this empty symbols here, which is a relation between, for example, for this geometry, which is a ribbon, and the plasmon energy, just the dispersion relation for different levels of doping. Okay, but the material is not homogeneous. It can have atomistic effects, and this is what we explore here. So if you consider the edges of the structure, then something happens when the plasmon energy goes above the Fermi energy, the doping Fermi energy, and then the plasmon gets essentially destroyed in realistic calculations. So by coupling to edge states, essentially. So likewise, there's this third harmonic generation and Kerr effect. You can describe them in a similar fashion, classically, or also with these atomistic models, and then you find differences, particularly for the Kerr effect. The difference is dramatic. Another feature of graphene is you can produce a huge field enhancement. I mentioned before the 10 to the 5 field enhancement in these nanostars with a single molecule binding to a metal surface. And now here, through realistic simulations, ab initio simulations, we predict 10 to the 8 intensity enhancement. So it's much higher than any other known material. I will spend a few minutes just discussing one of the few applications of these materials, experimental applications. Now, you can tune the plasmons by applying a voltage to your material through a gate underneath. Now, if you put molecules near this material, what will happen is that these plasmons can overlap with the absorption features, absorption resonances of the molecules. And therefore, even if the molecule is showing features at different frequencies, you can tune the plasmon so that they overlap. And by doing that, you are more sensitive to the presence of the molecules. So essentially, this is an application towards sensing, and then the idea is to become ultra-sensitive. So you can detect minute amounts of material. Now, these are the response of the ribbons. The dashed curves here are the ribbons without the molecules. The solid curves are the ribbons with the molecules. So one thing that happens is when you put the molecules, the resonances move to the red. And that's a typical effect because you put the electric close to any optical resonances and it moves towards the red. And on top of that, then you see the molecules leave some traces here, these features here. And these features are connected to amide 1 and 2 resonances in proteins. Now we do simple theory. That's why I insisted before. The theory to describe this material, because it's electrostatic, etc., is really simple. It's no more than this. And then you get the same, you can explain the same features, all of this. And because of this, you can not only that, but also, well, you have to fit here the Fermi energy. You know the applied voltage, but you don't know the Fermi energy in this particular application. So you have to fit it to in the calculations. And then the fitted Fermi energy and the applied voltage, you plot them here, and they show this relation. It's like the Fermi energy goes like the square root of the voltage, and that's what's expected for electrostatic doping of a material. So we believe we are doing things correctly. And then another thing is that we can actually fit the parameters, the conductivity of this structure, and also find what is intrinsic about the response of the molecules. And by doing that, you can deduce what is the electric function of the molecules, which is this one, using the graphene. And this is now compared with other measurements of direct infrared absorption for the molecules. But in this case, the infrared absorption, it requires many, many more molecules to do the same experiment. So what we gain here is that much less number of molecules are required to do these measurements. In view of time, I think I will skip the next 2 or 3 slides. And then, yes. One more thing that we have been discussing is what is the when you hit graphene, then something that happens is when you hit graphene, something that happens is that you can thermally populate the plasmons, and if you thermally populate the plasmons, they will emit radiation. This is something else that has been is being heavily investigated now. Just for the production of new terahertz sources, no? Where there's always a demand for new terahertz sources because of the difficult range. One more thing is quantum optics with plasmonic structures. So you can consider a quantum optical emitter, for example, a two-level system, placed in the vicinity of a plasmonic structure, and then with graphene, because of the confinement of the plasmons, and also because of the lifetime of these plasmons, which is much more than in other plasmonic structures, then you can have a situation where the interaction, the coupling rate of the quantum emitter to the plasmon back and forth is higher than the decay rate of the plasmon. So when the coupling rate, basically during the lifetime of the plasmon, you have this excitation can go back and forth several times. Okay? When you do that, then you are in the strong coupling regime. That's very difficult to achieve in quantum optics. Now, graphene is actually a candidate to achieve this strong coupling regime in a robust solid state environment without the need of expensive equipment. So, then you can do various things, for example, coupling hybridizing the plasmon, the two-level system with the plasmonic, with the plasmon in the material, and that gives rise to quantum nonlinearities, nonlinear response inherited from the the quantum emitter, but also quantum statistics in the second order correlation function. We have been postulating that because of the different frequency scales that are involved in the plasmon frequency, the decay rate, the rate at which you can dope the material, the gigahertz with microelectronics, the decay rate of an emitter, for example, erbium, and when you put it close to graphene, then the decay rate goes much, much higher. Essentially, you can control the decay rate of an emitter at will just by operating, by changing the doping of the material. And the last point I want to touch in just a couple of minutes is most of the results I've been showing are in the mid-infrared. This is very important for sensing, but if you want to do other applications, like for example, optical signal processing or other forms of sensing, you need visible and near-infrared frequency ranges. That is not 0.1 eV, but something like 0.5 or 1 eV photon energy. So we saw that the plasmon energy, plasmon frequency scales like this with the doping and the size of the structure. So obviously you can change the doping to much higher levels, but that's difficult. The one thing you can do is actually reduce, you can shrink the structures and make them smaller. How small? So you can do self-assembly, like in this work from Klaus Mühlen, where they do a self-assembly of molecular precursors to form ribbons. So ribbons that are nanometers in size. Eventually, when you decrease the size even more, you reach things that look like graphene but are not graphene, which is these molecules. So this is triphenylene, is like a small version of graphene, but it behaves the same. So if you have the material without any doping, then you don't have any resonance. If you put one electron or one hole, then you have a resonance in the visible. Okay? So it's essentially the same as graphene. And then we understand these resonances are plasmonic analogs in molecules. Essentially, you have a molecule, you put an electron, for example, in the molecule, you oxidize, and then light can probe the molecule and excite a molecular plasmon that was not available before without the charge. You can do this electron transfer through a gate in an electrolytic solution, and this is actually something that was done in the group of Naomi Hallas and Peter Norlander. So these are different molecules that they used. So the spectra in gray color are without the doping, and now when you put some doping, then the spectra change a lot, and so you can see visible changes in color in these molecules. So you can see them by bare eye. So essentially by putting, well, actually this is theory that explains reasonably well, qualitatively, the different spectra. In fact, you need to do a better job, then you need to include the phonons, and that's what's done here. And then we believe these are plasmons, among other things, because they have dependence on the environment. For example, you put a solvent with a different index of refraction, they change the frequency as one would expect. So you increase the index of refraction, then the resonance goes to the red shifts. And finally, this is a device, an electrochromic device that was made out of these ideas. So putting the molecules inside a gel and just doping them in this gate configuration. And so you can see changes in color by just applying a voltage there. Okay. So I think with that I would like to conclude. Just I leave you some suggested things to read here. And these are the members of my group. Again, I welcome you to apply to positions at ICFO. I must advertise that. So thank you very much for your attention.
Thank you very much for a stimulating talk. Are there any questions? It's okay. He's a nice guy. All right, I have a question. So you said you went from the sheet graphene, and then at some point you said that when you try to do it with a ribbon, that the edges will destroy the plasmons, if I got it right. Then at the end, you actually said that if you go to very small pieces, so dittraction and things like that, then you sort of have plasmons again. So regarding to that, maybe a two-folded question. First of all, what if you somehow mitigate the edges, if you make it three-dimensional or Möbius strip or something like that, would that help to sort of to keep the plasmon in your particle? And why does the plasmon come back when you reduce the molecule to a molecular size?
Actually, there is a way of getting rid of the edges, like in carbon nanotubes. They don't have edges, right? So infinite carbon nanotubes, instead of a ribbon with edges, you just close it, and so it doesn't have edges. And indeed, these carbon nanotubes also support plasmons, have been recently measured, by the way. And then it supports plasmons when doped, okay? However, the connection to here, as a figure of, that is interesting to keep in mind, the doping that you get for 1 eV doping, no, of change in Fermi energy, which is a lot, no? You achieve that by putting of the order of 1 electron every 50 atoms, 50 carbon atoms. So you put 1 extra electron every 50 carbon atoms, okay? In this molecule, so you have 18 carbon atoms, and you put 1 electron or a hole.
If you
squeeze
it with a lot of electrons, then you can still have the effect.
It's a massive effect. It's a massive effect. But then what I wanted to say here is that in this case, now what destroys the plasmon is when it goes above the Fermi level. So if it's 1.2 eV here, boom, or 0.8 eV, when it goes above it. In the case of the molecules, the equivalent Fermi level would be so high that, it's actually depends on the specifics of the electronic balance structure of the molecule, the electronic states of the molecule. So that's what makes it, I think, come back.
All right.
Okay.
That was my okay, so you do have plasmons and nanotubes that has been then demonstrated.
Yeah.
Fullerenes?
In
a fullerene? C60, buckyball?
Oh yeah, but in that case, I don't know about we have predicted that you have plasmons in doped C60s that are different from the plasmon that you already have in undoped C60s. The plasmons in doped C60s, I think I put at the beginning, so those were measured 20 years ago or so, or more. Yeah, here it is. So over 20 years ago, no? Right? So these are plasmons, the pi plasmons. Okay, so 60 electrons here, they form a plasmon. No? If you dope it, then you have another plasmon here as well, something else. No? To my knowledge, that has not been yet done with doping.
Right.
So it's like C60 radicals.
Thank you.
Okay.
More questions from the audience this time, please. I know you can come up with one question. Okay, I can keep asking questions. About your sensor applications, you said they were very sensitive when you attach the protein to the let's say to the graphene sheet, and then you can tune to change the voltage and get into the resonance nicely. Are they also very so they are very sensitive? Can they also be used to discriminate between two types of molecules? Because so sensitivity is one thing, but selectivity is a little bit the other. So
yeah, I think that's difficult because then, essentially you can discriminate between, here it is, no? You can discriminate between the relative weight of these two amide groups, right? So the relative weight might give you some indication what type of molecule you have, no? But it's difficult to be completely specific.
The proteins will probably always look more or less the same.
Yes, so I think in order to, yeah, more or less. So in order to be selective, I think you have to use some sort of marker or some molecular marker so that only your target molecules stick to the graphene or, yeah.